In previous video, we explored how researchers tackle the challenge of training large language model using technique called sharding. We also calculated the memory requirement for those models using GPT-2 as an example. Though GPT-2 is now 5 years old, it still requires enormous amount of memory and we know exactly how much. But this naturally leads us an equally important question. How many operations per second are required to train these LLMs? In this video, we'll see what are FLOPS and how it is responsible for the rate of training machine learning models. Operations per second, commonly known as FLOPS or floating point operations per second, measure how many arithmetic operations a piece of hardware can perform in 1 second. You'll frequently encounter FLOPS specification when examining GPU capabilities. To put this in perspective, let's break down what are these measurement means. One flop represents a single floating point operation, like adding two numbers. 1 gigaflops means a hardware can perform 10 raised to the power 9 operations per second. And respectively, these are for teraflops and petaflops. A flops consist of entire operation from loading the data from memory, perform computation and storing result back to the memory location is considered as one flop. So the above numbers are just raw computation capability of hardware, but in real world other factors can affect efficiency like speed and bandwidth of memory. So let's calculate the computational requirement for training model like GPT-3 which has 175 billion parameter to understand the scale of operations involved. Before diving into the calculations, here are the key specifications of GPT-3. To calculate the total number of operations required to train a 175 billion parameter of GPT-3 model with a batch size of 3.8 million tokens, we need to break the process into forward and backward pass. This includes the following. And here are GPT-3 specifications. We know it has number of parameters which is 175 billion. It has 96 number of layers and this number of hidden dimension. It has also 96 number of attention head and it is trained on 3.8 million tokens of batch size and on 300 billion tokens of dataset. GPT-3 is having 96 layer and here are the key components of each layer. Self-attention mechanism which computes the attention score and update the token representation. Feed-forward network which includes linear transformations and activations and layer normalization. And here are the symbols and its meaning which we will use in our calculation. Now that we know all components, let's start calculating operations required per component. First, let's calculate for a self-attention layer. Now self-attention can be break down into its subcomponent and we'll do a detailed calculation for this. First step of self-attention mechanism is to compute key, query and value projection. This is the step where embeddings are transformed into different matrices. So the calculation of projection will be 3 times batch size times square of dimension of hidden layer of model. Since we know the value of batch size and dimension of the model, we can substitute the values here. And performing the calculation, we'll get the values. The second step is to compute the attention score. The attention scores are computed by performing a dot product operation between query and key matrices. Then softmax is applied to the attention score for each token. So substituting the values in this formula and we have this value. Now the weighted sum of values which is softmax of query key and value. The attention scores are multiplied with the value matrix to compute the weighted sum. And then the output of weighted sum is projected back to the original token dimension. So here are the flops required for computing self-attention. To sum them up, we'll get this. Now that we have calculated operations required for self-attention, now we are ready to move to next step, which is calculating operations required for feed-forward network. The feed-forward network consists of two linear layers with hidden dimension of 4 times the dimension of hidden layer. First, the linear layer. Then that will pass through GLU activation function. Then the second linear layer. And then we'll sum them up to get the total number of operations required for feed-forward network. Now, for layer normalization, which is applied before the self-attention and feed-forward network, which is this, which is total number of operation for layer normalization per layer. Similarly, we can calculate element-wise addition of tensor to get the operations required for residual connection. Then we can calculate the operations required for per transformer layer, which is the sum of self-attention plus feed-forward plus layer normalization and the residual connection. Once it's done, we can calculate the operation required for forward pass. which is the product of number of layers and the operations required per layer. Now we saw the detailed breakdown of forward pass calculations, and backward pass is generally 2 to 3 times more expensive than forward pass. I'm not going to break down calculation for this, otherwise the video will stretch long unnecessary. So we are safely assuming 2.5 times of the forward pass calculation, and we can calculate backward pass based on that. Now since we have number of operations required to compute for forward and backward, by adding them together we'll have the total number of approximated operation is required to take one step of training. This total operation is for one training step, but we already knew that GPT-3 was trained on 300 billion token for 2 epochs. So to get the steps required for each epoch, we'll divide the 300 billion tokens with the batch size, and we'll get 78,947 steps per epoch. Now that we know how many steps required for each epoch, let's calculate the total number of operations required for training for 2 epochs. So for that, we'll take the total number of operations times steps per epoch times 2, and we'll get the total number of operations required to train the model for 2 epoch. Can you believe it? Seriously, can you believe it? Even though I take a very rough estimation of backward pass and ignore other minor operations, the number is this much big. Let's see how much big it is and how much time and resource it will cost you if you plan to train such model. Suppose if you have NVIDIA's A100 GPU, which is capable of performing 624 teraflops for mixed precision, which is 16-bit floating point operation, how much time it would take to run this model? So the time required for this will be the total number of operations divided by the computation capability of A100, and we'll get this much hours. This much is equal to 12,827 days or 421 months or 35 years on a single A100 GPU. So how much resource it will cost you if you wanted to finish the training in 1 month? So if you are ready to train day and night, then you can take total GPU hours and divide it by the timeline. In our case, it's 30 days. And hence, you'll need roughly 856 GPUs to finish the training in 1 month. And now you know the reason behind why NVIDIA is world's most richest company. Here are 3 things to remember from this video. Flops are not only dependent on the computation hardware, but instead the rate is dependent of the memory speed and bandwidth as well. The complete training process needs this much operation, which would take 35 years on a single GPU, a clear illustration of why individual researchers or small organizations cannot easily train these models. The actual number of operations required for training such models are actually much large because of more operations in between, such as residual connection, embedding computation and all, which we didn't consider in all calculation.